to this lecture about load curves and combinations of generators. In this lecture, you are going to discover how a certain extent of overlap in heat and cold generators may help with the control of temperature and energy usage and costs. You may remember a lecture in week 1 or in the course Energy Demand in Buildings, where we show that by making hourly calculations over a full year, it is quite easy to determine the heating and cooling load profiles of a building. We also saw that the nominal load was the maximum one and the annual energy used is the sum of all 8,760 hourly loads, which is the same as the area under the curve. In this slide, you see an example of a very large office building of 13,000 square meter floor area, such a building of 10 floors, 71 meter length and 18 meter width. You see that there are some high peaks, but that they only appear a few times in a year. The annual heating demand is 854 megawatt hour and the nominal heating load is 421 kilowatt. For cooling, the building needs 297.5 megawatt hour and the cooling load is 921 kilowatt. You also may remind that the costs of equipment depend on its nominal load. Therefore, on a maximum load, this equipment should deliver, which is here 421 kilowatt heating and 921 cooling. And you see here that most of the time the equipment will work in partial load, far below the maximum load. To analyze these partial loads, it is useful to draw a load curve. It is very easy to do, you just need to sort all yearly data from the largest to the smallest one and to draw again the figure. I did it in Excel. You recognize the nominal loads, this time at the start of the curve. The annual heating and cooling demands can still be found as the sum of all heating loads, which is the same as the surface area under the curve. You also see now clearly that heating is needed for 5,300 hours over a complete year and the cooling only for 1,200 hours. This is because the building is located in a moderate cold climate. How to read such a load curve? I will now zoom a bit in, leaving out the hours without heating or cooling. Let's look at the heating first and take a load of 100 kilowatt. The diagram tells us that during 3,500 hours of the 5,300, that is 66% of the time, the load will be higher than 100 kilowatt. So during 1,808 hours, 44% of the time, the load will be lower. Let's now take a load of 350 kilowatt, corresponding to 83% of the total power. During 55 hours a year, the load will be higher, which is only 55 divided by 5,300 is 1% of the time. So 99% of time the load will be lower. It is a bit difficult to see like that, to see it on the curve, but if you would sum up all these 99% loads that are below 350 kilowatt, you would see that we can cover 97% of the total heating energy demand. That's the red surface. The only thing it does not cover is that little bit above. If you look now at the load duration curve for cooling, we see that it has a bit different shape. Let's take now again 83% of the nominal load. So 83% of 921 kilowatt, which is 764 kilowatt. The blue area under the curve represents the cooling energy demand covered by this power of 764 kilowatt. If we would sum up all hourly loads smaller than 764, we would find that 95% of the total cooling demand is covered by this power. The message here is that the relationship between the load and the corresponding energy demand is not linear. In both heating and cooling cases, with a load of 83% of the nominal one, we were able to cover more than 95% of the total energy demand. And this is a very interesting feature when sizing HVAC equipment in relation to its price. The first column in this table shows an example of price of diverse generators. Be aware that these prices may change quickly and may not be representative of prices in your region. But the point here is that there are large price differences between technologies. The price is given in euro per kilowatt, so the price is a direct function of the nominal load. The second column gives the assumed efficiency of the technology. The idea is that when a technology, like heat pump, is very efficient but expensive, it could be worth to buy a smaller heat pump, for instance only 83% of the needed nominal load, covering this way 97% of the total energy demand. And for the remaining 3%, we could buy a less expensive device like an electrical heater at the expense of its much lower efficiency, but that's only for 3% of the total. You see now on the right the worked out example for the building under consideration. If we use only a heat pump with nominal power 421 kilowatt, then the investment is the price per kilowatt, 1500 times 421, which is 631,500 euros. The electricity used annually by this heat pump is the total heating demand, 854,000 divided by the SCOP, which is 4, leading to the use of 213,500 kilowatt hour. If we now buy, as proposed earlier, a heat pump of only 350 kilowatt and use a cheap electrical resistance heating of 71 kilowatt, summing up to 421 kilowatt, the total investment is the one for the heat pump plus the one for the electrical resistance, amounting 527,130 euro. An electrical resistance has an efficiency of 1, 97% of the heating demand is covered by the heat pump and 3% by the resistance, so we come to a total of 232,715 kilowatt-hour electricity. If we compare both results, we see that in the second case, the investment is 16.5% lower, which is considerable, while the electricity use has increased by 9% only. Depending on the price of electricity, this may be worth doing it, but be aware that it may be financially attractive. However, in terms of environment and resource depletion, it is not very good. 9% more electricity is used. However, in this exercise, we did not account for the fact that the COP of many heat pumps and chillers decreases at high heating and cooling loads. The COP of a ground source heat pump may stay quite constant also at partial load because the temperature of the ground is quite constant, so the heat pump has to bridge all time the same temperature difference between the ground and the supply temperature of the floor heating, for instance. The COP of an air heat pump, on the contrary, varies a lot with the load. High loads take place when it is cold outside, so at high loads the heat pump must bridge a high temperature difference between the outdoor air and the indoor air, and its COP is very low. In the course Energy Supply for Buildings, we show how much the COP would drop. Imagine now that we have an air heat pump with COP 2.5 at normal load and a COP of 1.5 in peak load. What does that mean for the annual electricity use? The investment have not changed. With the heat pump only, I now account for the 3% peak demand that is covered with a lower COP, leading to an electricity use of 348,432 kilowatt-hour. We do it again for the combination heat pump plus electrical resistance, leading to 356,972 kilowatt-hour. The difference in electricity use is now much lower, only 2.5%, and this becomes an even more attractive alternative as the investment is much lower and electricity use hardly increases. In fact, in many air heat pumps, an electrical resistance is already integrated in the heat pump. For chillers, the problem is different, as there is no alternative technology to cover the peak demand. You remember that to generate cold, only cooling machines can be used, or low-temperature passive technologies like evaporative cooling and natural sources of cold like ground or surface water and aquifer thermal storage. But these renewable technologies do not work at high loads because their temperature is relatively high. So for chillers, either you do the full load and accept the price, or you do a bit less, like that, and just accept that for 5% of the hours it will be too warm in the building. This is mainly done in moderate climate countries and is sometimes referred to as top cooling, which is very confusing as it does not cool the top. What can be done is to use a renewable cold source as basic cooling instead of for peak and use the chiller above a certain load. This way, a maximum use of environmental cold can be achieved, for instance, like here. The nice thing is that ATES technology, or the use of surface water or of night air, is not very expensive. In fact, it may be cheaper than a chiller. In well-insulated office buildings in moderate climates, there is already a high cooling demand in spring or autumn, while the outdoor air is still cool. In that case, the outdoor air itself can be used for the base load. In a PNID, the configuration we studied for the heat pump would look like that. Let's start from the room on the right of the picture. Instead of the room, it may also be the heat delivery to the air handling unit. The water in the radiator is cooled down by heating the rooms and flows back to the heat pump, the purple arrow. In the heat pump, it is heated to a certain temperature. If the temperature is high enough, it goes directly to the room or air handling unit. If the temperature is too low, it goes to the gas boiler or electrical resistance, is heated further, and goes then to the room or air handling unit. So, in this part here, there is a controller deciding where the water should go. For a chiller, combined with the use of environmental cold, what we call free cooling or passive cooling through ground, water or fresh outdoor air, it would look like that. Let's start here again from the right at room or air handling unit level. The water in the AHU or the ceiling cooling cools the room and is therefore heated and flows back to the environmental cold heat exchanger to be cooled down. That's the orange line below. If the temperature is low enough, it goes back to the room. If it is not, it is sent to the chiller to be cooled further before going to the room. Just like for the heat pump, at this place there is a controller deciding what to do according to the temperature. Observe that here there is a bypass in case the environmental cold has a too high temperature and cannot be used for cooling. When choosing generators, it may also be good to think about failure and maintenance. If there is only one boiler or chiller and there is a technical failure, then there is no heating or cooling at all in the building. If the total load is divided between more generators, it is likely that at least a few of them keep working and that they do not fail all simultaneously. It makes also maintenance more easy. You can switch off one generator to maintain it while keeping the other ones running. That will give much less burden to the occupants. When more generators are used next to each other, we talk about cascading. In general, it will be done in parallel, like this. So that is different from what we described in previous slide, where the additional generator was connected in series. So, in this lecture we described how to set up load duration curves and how to use them to play with combinations of generators in order to decrease investments while ensuring a high efficiency. And we went into more details about air heat pumps and chillers, for which this is particularly important. We then described the P&IDs corresponding to the use of multiple generators and looked at how they are connected to each other. And finally, we described how the use of more but smaller generators may be useful for maintenance. Thank you for your attention. Goodbye.